Hi, all students. Today we will continue on the energy balance. That's right. Last lecture, I talked to you how to balance the energy for the closed system and open system. But now we will talk about the system with water or steam table. And for this case, if we would like to know what is internal energy, what is the enthalpy of the process material. For the internal energy, enthalpy, we cannot know or we cannot measure the absolute value of the specific internal energy and enthalpy. That's right. But we can determine the change in internal energy or enthalpy but corresponding to a specific change state, temperature and pressure. That means the convenient way to interpret or to calculate or to measure change in specific internal energy and enthalpy. It should temperature, pressure, or state of aggregation. We call it as the reference state. That means we have to choose and reference state to calculate the change in enthalpy and entropy. Right? Okay. What is the reference state? I will give you an example for this. Example, right? The enthalpy change. Please remember enthalpy equal to internal energy plus for work. That's right. S equal to U plus PV. Right? This is the formula for enthalpy. Okay. For this case, if we would like to calculate the change of enthalpy for carbon monoxide going from a reference state measured with the following result. For example, right, from carbon monoxide gas at 0 degrees Celsius at 1 atm to carbon monoxide gas at 100 Celsius 1 atm. The data S1 equal to 2,919 Joule per mole. And also, carbon monoxide gas at 0 degrees Celsius 1 atm to carbon monoxide gas at 500 Celsius to 1 atm. Because it's delta 2 equal to 15,060 Joule per mole. Right? Then we cannot calculate absolute enthalpy or absolute specific enthalpy. For the convenient, we may assign H0 equal to 0. Right? H0 equal to 0 to reference. For that means delta S1. For this case, delta S1 is right? Delta S1 equal to delta S1 equal to S1 minus S2, right? Or delta S1 minus 0 equal to S1. And also delta S2 equal to S2 minus 0. For this case, we reference that delta S1 equal to S1 minus S0. Delta S2 equal to S2 minus S0. But for this case, the S0 is reference state. For the reference state, we assign the value at 0. For that case, for example, right, at temperature 0, 100, 500, enthalpy is 0. Because delta S0 means delta S0 reference to 0 degrees Celsius. S0 minus S0 equal to 0. Delta S at 100 means delta S 100 delta S 100 means S 100 minus S 0 degrees Celsius equal to 2,919 minus 0. And also, if we calculate delta S at 500, for this case, we reference to 0 degrees Celsius means S at 500 minus S at 0 degrees Celsius equal to 15,060 minus 0. For that case, if we choose one state, in reference, we have to assign 0 value for that case. 0 value enthalpy. Right. Okay. We can say that the specific enthalpy of carbon dioxide at 100 degrees Celsius and 1 atm. This is relative to carbon dioxide at 0 Celsius, 1 atm, equal to 2,919 Joule per mole. This means that the change of enthalpy, right? The change of enthalpy of carbon dioxide at 100 reference to 0 degrees Celsius is delta S. It is the property that because we cannot measure the pure or absolute enthalpy. Right? For example, right, the following entries are taken from data table for saturated methyl chloride. Okay. This for the state at liquid temperature is minus 40, pressure, specific volume, specific enthalpy, and vapor. This case, for this case, we can get that the reference state should be liquid at minus 40 Fahrenheit because its enthalpy equal to 0. That's right. Enthalpy equal to 0. And also, the vapor equal to 196.2 T. We reference this. That's right. We may be reference for this case. Okay, for example, right? What the reference state, what you to generate given enthalpy. For this case, the reference state is liquid at minus 40 Fahrenheit and pressure is 6.878 psia. Because the enthalpy is 0. Enthalpy is 0 means this state is the reference state, right? Because S equal to 0. Okay. For this case, I can say that the reference state is liquid at minus 40. Okay, the second question, calculate delta S and delta U for the transition of saturated methyl chloride vapor from 50 to 0 Fahrenheit. 50 to 0 Fahrenheit. For this case, mean S at 0 minus S at 50. Right? S at my 0 minus S 50. 0 is vapor is 196.23 minus 202.28. Right? You get this value. Please note that what is the enthalpy at 0 Fahrenheit? Enthalpy at 0 Fahrenheit is the enthalpy referring to liquid at 40 minus 40. That's right. Because like 196.23 is the enthalpy of vapor methyl chloride, right, relative to the methyl chloride liquid phase at minus 40 degrees Fahrenheit. Right? Because it's 0S. Okay. And also the same. S at 50 Fahrenheit. F at 50 Fahrenheit mean S at 50 Fahrenheit minus S at minus 40 because we reference to minus 40. S minus 40 equal to 0. That means 202.28. And then you can calculate the delta S between 0 and 50 or 50 and 0. Okay, you can substitute this. You get the difference. Because this term reference to liquid at minus 40. This term is referring to liquid at minus 40 already. Okay. The second one, we can calculate delta U because you know delta S. You can calculate delta U. Delta S equal to U plus PV. Delta S equal to delta U plus delta PV. And then you can calculate delta U is equal to delta S minus delta PV. You know P, you know V, that's right. Okay. As delta S minus P final, V final, minus V initial, This is delta V, delta PV, that's right. For this case, we reference 50 to 0. This means V at 0, V at 0 minus P at 50, V at 50. That you substitute. P final is 18.90. V final is 4.969, right? And V initial is 51.99. V final, V initial is 1.92, and then you get this value. Right? You get this minus 4.96 BTU per pound is delta U. Right? Okay. For the last question, what assumption did you make in solving equation 2 regarding the effect of pressure on specific enthalpy? As we would assume independent of pressure. We assume that it not depend on the pressure. It's not depend on the pressure. Because we thought that the pressure change, that there is not change. For that case, like this table. The steam table, right? The steam table, we talk about the vapor, liquid, and solid form, which we talked you earlier in the multi-phase system. Multi-phase system, for example, a PET diagram, it is solid, is a subcooled liquid or liquid phase. It's a superheat state. And this line is the equilibrium of set liquid and set vapor or set steam. And this set solid and set liquid. This set vapor and set. In this case, mostly we talk about the steam table is the vapor liquid equilibrium, set liquid and set steam. With the reference state of the property of the steam table is referent to the triple point here. Triple point means the three phase is this point. We have three phase in this point. This is the steam table of saturated steam in the water vapor. That's why it's water. This is the first column is temperature. And this is the pressure. This is the specific volume, is specific internal energy, specific enthalpy. It's water and steam. Water and steam mean that liquid, that steam, that liquid, steam. In equilibrium. It is that water, that steam. It's also that water and that steam. It is that internal energy of that liquid, internal energy of that steam. It's also specific volume of that water, specific volume of that steam. It's liquid phase. But for the enthalpy, we have three columns. The first column for enthalpy is the enthalpy of that liquid. The last column is enthalpy of that steam or that vapor. Right? And the middle means the evaporation, heat of vaporization. Right? Heat of vaporization. And also you can calculate based on the difference between enthalpy of that steam minus enthalpy of that water. Like for example, right, the that steam is 2005 less than 1.6 minus 0, you get this. And the second one at 2 Celsius, that's right, at 2 Celsius. 2005 less than 5.2 minus 8.4, we get this. The heat vaporization is equal to enthalpy of such steam minus enthalpy of such water. These are the steam table. This is based on the first column is temperature. For this case, at saturation, is saturation, and also we start at liquid. The temperature is the boiling point. The boiling point is the first bubble that occurs in the liquid phase, right, for evaporation. This is also the property of steam table, but we start with pressure. It's the same period table, but period table it is start with temperature. In this case, you know temperature, you know pressure. In this case, you know pressure, you know temperature, you know specific volume, specific internal energy, enthalpy. It's the same, but first column is pressure, the second column is temperature. Is opposite. And the next table is a steam table for superheat steam. Superheat steam is the steam is located in this zone. That's right, this zone. It's also vapor, only vapor. In this case, the first column we talk is the pressure in bar, and in the bracket is the temperature is set. At such steam or temperature lower than superheat, the bracket temperature is boiling point. For this case, it's the latter. That's right. This zone is liquid, and equilibrium in set steam. And this zone is superheat steam. Right, superheat steam. Okay. Heat steam. Okay, for example, right, if you talk about at 0 bar, right, at 0 bar, the temperature at 50 Celsius is superheat. That's right. It also superheat. If you talk about 0.5 bar, 0.5 bar, right, at 50 Celsius, it is liquid, equilibrium with vapor. It's set liquid and set vapor. You can calculate, right, the property of the set water and set steam. It's the set water and set steam. Set water and set steam is at 81.3 degrees Celsius. And also you can calculate the property of enthalpy, internal energy, specific volume at 50, at 75, and at 100. For at 100, it is the superheat. This is the superheat at 100 degrees Celsius, 0.5 bar. The temperature in the bucket is not boiling point, it's dew point. That's right. For this case, it's dew point because the system is only vapor phase. And also for 5 bar, that's right. 5 bar, the set temperature is 151.8. And then the property at that solution is the enthalpy of that liquid, enthalpy of that steam, internal energy of that liquid, energy of that steam, like this. And also at 50, 25, 100, 150, this is also the liquid, right? Liquid phase. It should be subcooled liquid, because it is set steam and set water like this. For this case, the temperature in the bucket is boiling point, but at 200, 250, 300, 350, right, it is superheat. The set temperature is dew point temperature. That's dew point temperature. And the property of HUV is HUV, right, for 200, HUV for 250. Right? For another is at higher temperature. This is the same table. Is 350. For the temperature higher 350 is all of this superheat state. Superheat. This is superheat. Only vapor in higher than the saturated state. For the saturated temperature in the bucket, this is the dew point temperature. For example, right, determine the vapor pressure, specific internal energy, specific enthalpy of such steam at 133.5 degrees Celsius. You can open this table. Open this table. It's at temperature is 133.5. The temperature is the vapor pressure is 3 bar. This is 3 bar. Specific volume, specific internal energy, specific enthalpy. This specific volume. In this case, is offset steam. That's right. Offset steam with the vapor phase insaturated with liquid phase. This is for that liquid. For this case, we ask for steam 0.6 kilo6 specific volume. Specific internal energy is 2,543 kilojoule per kilogram, and steam, yes, it is 2,724.7 kilojoule per kilogram. Specific enthalpy. It is the first question for question 1. How about question 2? Show that water at 400 degrees Celsius and 10 bar is superheat state, and determine its specific volume, specific internal energy, specific enthalpy relative to liquid water at the tip point. For this case, at higher temperature than 350, you have to use the table B7. And this is sure it's a superheat, right? Heat at 10 bar at 400 is a superheat. Because as lower than this, there is no 400 degrees Celsius. And it's sure it's for the superheat state. That's right, the saturated temperature is 179.9 Celsius. It is a superheat. And also, the property, right? Enthalpy, internal energy, specific volume, and dew point temperature. Dew point temperature is the saturated temperature in the bucket. Can you see this table, right? This is the specific enthalpy, specific internal energy, specific volume. That is the answer. And the last one, show Specific internal energy, specific enthalpy for superheat steam depends strongly on temperature and relative slightly on pressure. This depends strongly in temperature, but independent of pressure or depends slightly with pressure. Look at this. At heat steam. When the temperature change, for example, right, U and S, 400, 450, 500, 32, 46, 33, 34, 5. That's 9. It's strong dependent with temperature. It's strong with temperature. If you compare when the pressure increase, this is P2, 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 P2. That's right. It should be slightly depend on pressure, but strongly depend on temperature because it's a 2,200, 3,200, 3,200, 3,200 is about 80. 80 is the same. That's right. At 0 to 0.1. 0.5, 80, 79 is only 1. Right? 1 is the same, about 79, 78. 5, 72, 10, 64. That's right. It slightly change when the temperature, when the pressure change, but strongly change with pressure change. That's right. 200, 3,200, 3,300, 3,400, 3,500, 3,600, 800. It's clearly enthalpy is strong dependent with temperature, but slightly dependent with the pressure. Answer for the question. Answer for this question already. Next example, right? The energy balance on steam table, a steam turbine. That's right, steam turbine. The steam at 10 bar absolute with 190 Celsius. Surely superheat. That's right. If you back to this, 10 bar, 10 bar, 10 bar, 10 bar, 10 bar. 190 is close to 200. That is superheat. That's right. Because at 150 is liquid or subcooled liquid. This is 10 bar. That's right. 150, 200. But for this example, it's 190. It's close to 200. We can decide that it's superheat. That's right. But we don't know exactly because between 150, 200, we change from liquid to the superheat. But for this case, we assume it's close to 200 is maybe superheat. Of superheat. Oh, sorry, for this case, I something wrong. Steam at 10 bar absolute with 190 of superheat. This means the 190 greater than the set temperature. Set temperature. The set temperature for this case for 10 bar is 180, about 179.9. But this system, the temperature is higher than that temperature is 190 because the superheat. Superheat means the temperature is higher than the set temperature. It is equal to 29.9. That's right. Plus 190. For this case, is fit to a turbine at a rate of 2,000 kg per hour. M0 is the magnet. The turbine operates with adaptive operation. Adaptive operation, but there is no heat cross between any environment and system. There is no cube for the system. And the effluent is saturated steam at 1 bar. Calculate the work output of the turbine in kilowatt, neglect kinetic energy, neglect potential energy. For this case, you can use the general equation for energy balance, enthalpy plus delta kinetic energy plus delta potential energy equal to heat minus work. For this case, there is no kinetic energy, no potential energy, and no heat cross between environment and system. Also, you get delta S equal to minus delta delta S, sorry, W equal to minus delta S. And also delta S equal to m dot. M dot is the mass rate multiplied by specific enthalpy out minus specific enthalpy in. Right. Okay. For this case, why the heat drop because adiabatic. Adiabatic means heat is equal to 0. Okay, the first step you have to calculate what is the inlet stream and what is the outlet stream. The inlet stream is feed at 10 bar with superheat of 190. At 10 bar, the SAT is 179.9. Okay. And then you can calculate the inlet temperature. Inlet temperature is approximately 180 for SAT plus 190. You get 370 Celsius. For this case, you can determine the enthalpy at 10 bar and 320. That's right. In this case, because we reference to the triple point already, if you back to the double point table, in this case, the enthalpy for each term, this term is referring to 0.01 Celsius already as the triple point because the S is equal to 0. 33.6 is mean the difference between a Celsius and 0.01 Celsius. And also, 2501.6, this is referring to liquid water at 0.01 Celsius. Also. That's right. For this table, the property is referring to the triple point already. And enthalpy is also delta enthalpy. U also delta U, V also delta V. But because we reference, U also delta U, S also delta S, because we reference to the triple point at 0.01 Celsius already. That's okay. In this case, the delta S enthalpy at inlet is mean at the 370. That's right, at 10 bar. Okay, you back to the table. Okay. 10 bar. Right. 370 is located between 350 and 400. You have to interpolate. Or enthalpy is between these two values. Enthalpy is between these two values. You have to use the interpolation that I talked in the earlier of this class. How to interpolate. Most example and simple technique which you like linear interpolation. After you interpolation, you get the enthalpy is 3201. That's why it located between this value. 3201 kilojoule per kilogram. How about the outlet? Outlet temperature. The outlet at 1 bar. It's saturated steam, not superheat steam. Saturated steam at 1 bar. You have to open 1 bar and saturated steam. 1 bar. This is 1 bar. This 1 bar. The saturated, there is no saturation. There is no saturation. Okay. Okay. This is 1 bar. The unit table. Saturated system is 99.6 degrees Celsius. It's approximately 100 degrees Celsius. And then you get enthalpy is such steam, that's right. Such steam is 2675.4. And then you substitute S out, S in. S in. S out. Please note that S in is already referring to the triple point already. You can talk about delta S in, delta S out. Because delta S in equal to S in minus S at triple point. S at triple point is 0. You get S in equal to this value. And also S out means delta S out equal to S out minus S at triple point, but S at triple point is 0. You get S out equal to this value. And then you substitute S in and S out to this. You know mass rate is 2000 kilograms per hour. And then you calculate work, this mass rate, S out minus S in. And then you convert the unit of hour from 1 hour equal to 3600 seconds. And then you get 292 kilojoule per second. But you know, right? Joule per second is watt, and kilojoule per second is kilowatt. Get this? It's the work divided by system to the surrounding. That's right, to the surrounding with 292 kilowatt. Okay, I will conclude for you that the general energy balance procedure. The first step, you have to draw and label the flow chart. It's like the material balance, and you specify the information in the flow chart. Be sure that the flow chart includes all of the information. The first step, draw the flow chart and specify the information like input temperature, input flow rate, input amount, input specific enthalpy of each steam component. That's like temperature, pressure, enthalpy, and flow rate of mass or mole, like this. And the third step, you have to choose the reference state or state of application of the process. And then you determine the material balance and determine the energy balance. You have to balance both material balance and energy balance. That's right. Because the energy term, the first term in the energy in and energy out due to the flow, input and output of the steam. And you have to balance the mass also in the first step. For example, right, the energy balance on one component process. We have two streams of water are mixed to form the feed to a boiler. Process data are as follows. We have two streams. The first stream is 120 kilogram min of water at 30 Celsius. And the second stream is 175 kilogram per minute of water at 65 Celsius. At 65 Celsius. And output, that's right, output means the final state after you boil, you heat this temperature until it 7 bar. That's right, 17 bar. This is 17 bar. All of it in saturated state. And the excess steam emerged from the boiler to the pipe with 6 centimeter inner diameter. ID is the inner diameter pipe. Okay, calculate the required heat input to the boiler in kilojoule per minute. Right. For this case, you have to heat system, heat up the temperature. Okay, we have to add some heat. It's maybe from the heater, from electrical heater, something. Okay, for this, if the emergent steam is saturated at the boiler pressure, okay, and neglecting the kinetic energy of the inlet steam, there is no kinetic energy of inlet steam for this case. For the output, we have the kinetic energy, we have the flow. That's right. The first step, you have to determine the first or the flow rate of the or steam component using material balance. For this case, you have no material balance or not. The material is input, that's right, 120, 125. We have only one component, water. It's easy. That's right. Flow in, flow out equal. There is no generation, no consumption, and no accumulation. It's continuous steady state. That's right. And this balance. That's right. You can balance either. The output equal to 120 plus 175 equal to 280. Now you make the material balance already. The second step, determine the specific enthalpy of each steam. Because why we can determine? Because you know the input condition like temperature, output condition like pressure. Right? You can determine enthalpy input, enthalpy output. About enthalpy input, I will back to the table. Input at 30 and 35, 65. That's right. Okay, there is no information. We open. First case, you have to upload book already. That's right. It is a table in the appendix. Define. Steam table define. That's right. The first one is 75 degrees Celsius. How about the enthalpy of with water? The set liquid. That's right. 30. Okay. Liquid water is 125.7. Yes. 125.7. And how about 65? 65 is between 64 and 65, right? The value is between 267 and 276. That's right. It's located between these two values. Okay, you have to interpolate. It's approximately 271.9 kilojoule per. Okay, for this case, you know input at 30, you know input at 65, and then you calculate at output. Output is 17 bar. That's right. 17 bar. You have to see the second table. 17 bar. Okay. The 17 bar, the temperature is 204.3. This set temperature Celsius, and liquid enthalpy is 871.8. Right? And this is for vapor. That's right. The product is vapor. Okay, the product is vapor. The input is liquid, but the product is vapor. You have to read from the vapor. This is vapor phase. This is the liquid phase. That's why the vapor is 2793.4. This is. Now you know the information input output already for enthalpy input, enthalpy output. You know mass in, you know mass out. Right. And the final step, you do mass balance already, and then you can do the energy balance. That's right. The energy balance for this system, you can do the whole equation. That's right. Q minus W equal to delta S plus delta EK plus delta EP. This in terms of place of energy. We call Q dot W. S dot EK dot EP dot. Okay, for this, there is no work. This is a sharp work. There is no potential energy. Right. Because there is no the difference of the level. Okay. And finally, you get Q equal to delta S plus delta EK. Okay. Q equal to delta S plus delta EK. For this case, because delta S, we have three streams, that's right. Two input and one output. Delta S equal to summation of MISI of outlet stream minus summation of MISI of input stream. That's right. For this case, massless of outlet stream is 295. That's right. It's 295 kilogram per minute. Enthalpy of output is 2793. Is the output. And input we have two stream. First stream is 120 kilogram per minute multiplied by 125.7 kilojoule per gram. The second stream is 175 multiplied 271.9. And then you can calculate delta S equal to 7.61 multiplied 10 power t kilojoule per minute. And then you calculate EK. EK is equal to mu squared divided by m is mass, u is velocity. The first step, you have to calculate velocity. For this case, you can calculate velocity by dividing the volumetric or specific volume by area. Right? By area. And also you can determine the volumetric flow rate. Volumetric flow rate. About the volumetric flow rate for this case, volumetric flow rate equal to mass rate. That's right. Mass rate multiplied by specific volume. This is the V dot. That's right. This V dot. Okay. How to determine the specific volume? Specific volume you can open from the table that I forgot to show you, the table of the output stream at 7. That's right. If vapor, this is the steam. That's right. Specific volume of steam is 0.1166. Okay. And this is the specific volume of steam output. You multiply specific volume with mass rate. That's right. Mass rate is kilogram per minute. You multiply by cubic meter by kilogram. That's right. Kilogram cancel. And then you get cubic meter per minute. Then you change from minute to second. 60 seconds equal to 1 minute. And then you divide it by the area of the flow. Flow area because the tube, the flow in this direction, that perpendicular to this area, is the inside area, equal to pi r square. Right? Pi r square. The diameter of it is 6 centimeter. Okay, it's pi r equal to pi multiplied by r square. That's right. And then you change from centimeter to meter. That's right. 100 centimeter equal to 1 meter. Right? 10,000 square centimeter equal to 1 square meter. Okay. And then you can calculate area equal to 2.83 multiplied 10 power minus 3 square meter. And then you substitute this. Then you calculate the velocity, 202 meters per second. And then you calculate delta EK. Delta EK is the EK output minus EK input, but EK input is approach 0 because we neglect the kinetic energy of input state. Okay. Delta E equal to EK output state, outlet state, equal to m dot u square divided by 2. M dot is 290 kilogram per minute divided by 2. U is 202 meters per second is u square. And you know 1 Newton equal to 1 kilogram meter per second square. And also you know 1000 Newton meter equal to 1 kilojoule. And you calculate delta EK in terms of kilojoule per minute. And then you substitute EK. Right? You substitute delta S into this equation. You can calculate heat. That's right. Is add to the system. But heat you calculate heat equal to positive value mean heat add to the system. If you calculate heat is negative value, it means heat transfer from the system to the surrounding. For this case, heat is positive. Okay, heat add to the system is correct. That's right. Okay. For some comment, that's right. When the process stream contains several comments, the specific enthalpy of each component must be determined separately. But for the easy way, that's right, we can consider the mixture for near ideal gas or liquid with similar molecular structure for mixture of fluid. Then we can assume that the enthalpy for mixture component is the same as enthalpy for pure substance at the same temperature and pressure. That's right. This for some comment. Like this example, right, we have a liquid stream containing 60% ethane and 40% butane. That's in liquid phase. Its heat from 150 Kelvin to 200 Kelvin. That's is 150 to 200 Kelvin with a pressure of constant 5 bar. The pressure is constant 5 bar. After you read the problem, you have to draw the system also. We have the heater. Q should be input to the system. Okay. Calculate the required heat input. Calculate Q. Right. Per kilogram of the mixture, neglecting the potential and kinetic energy. For this case, there is no EP and EK. Okay. You have to use the separate enthalpy data for ethane and butane. Right. And then we can assume the mixture component enthalpy are the same for pure species of ethane and butane. That case. Okay. For the system, we have input the mixture of ethane and normal butane. The output also ethane and normal butane, but in the different way, right? From liquid to the vapor. Right? Feed in liquid, output is vapor feed. Okay. For this case, we base it at 1 kilogram per second of mixture. That's the basis of calculation. And you know the composition already of the feed. Right? You know temperature, you know pressure, you can calculate the the property is enthalpy in this case. And also there is in and out for mass 1 if you assume continuously flow. That's right, mass in equal to mass out. Right? Total mass is 1 gram and output also 1 kilogram per second. Input 1 kilogram, output 1 kilogram. It also mass is balanced already. That's right, mass is balanced already. And the same composition. The same composition because it's also ethane and butane, but for only we heat from 150 Kelvin to 200 Kelvin. Right. For this case, we have some energy balance. Now, the first step we have to determine enthalpy of ethane and butane input and output. Right. For this case, we'll talk about this. This is the superheat or saturated normal butane. Right. The superheat normal butane, the superheat ethane, and saturated ethane. You can open from this table. This is we collect from the Perry Chemical Engineering Handbook. Okay, for input, it's set liquid at 150 Kelvin or 5 bar. Okay, for this we have only the property input of normal-butane. It should be 150 like this. It should be this. For enthalpy of liquid, 29.4. This 29.4 input. This is for outlet. This is for inlet. Okay, this okay. Sorry. This is the superheat normal boiling butane. This butane. Butane is superheat is 30. That's right. Butane is 30. And for ethane, about ethane. This is ethane. 150. You use like the 5 bar for that case. And it's 14.3. Here at 14.3. This is the input component. And how the output at 2000 Kelvin. Right? This is 2000 Kelvin. This is 433.4. And 130.2. 130.2. This for the output. Please note that for the input it should be liquid, but the property is equal to the same. That's why we have 550. It should be about 30. That's right, about 29.44 and 30. That's right, for go to the same. That's like we should be at 30, and also at 150 is 314.3 and 313.7. It's go to the same for this case. This for 150, you use this value. That's why this is the input ethane, right? And this is input butane. This is output butane. This is output ethane. Okay, you know the value of this already. You call for the general energy balance. This is the general energy balance. For this case, there is no work. no kinetic energy, no potential energy, and then you get Q equal to delta U, delta S. Q equal to delta S. And you know, right, delta S equal to summation MI output steam minus summation MI of inlet steam. For output and inlet, we have two components. Right? For output, we have 60% ethane and 40% butane. That's right. 0.6, 0.4. And you know output of ethane, you know output of butane in the net value. That's right. This is minus input 0.6 ethane multiplied enthalpy and 0.5 ethane butane multiplied 30 enthalpy of butane input. And then you calculate 112 kilojoule per second. This is the Q, but for this the answer should be calculate the enthalpy or heat per kilogram of mixture. The kilogram of mixture input is 1 kilogram per second. And then you divide this by 1 kilogram per second, you get kilogram per 112 kilogram per joule per. For this example, right? Another example for the internal energy balance. Okay, for this case, the last example we will show you the simultaneous material energy balance. For this case, you cannot use the material balance only. You cannot solve bioenergy balance only. We have to spontaneous of both material and energy balance. For this system, we have the saturated steam at 1 atm, right? Discharge from a turbine at a rate of 1,150 kg per hour. This is of steam, right? And also superheat steam at 3 Celsius, 300 Celsius, 1 atm is needed at a feed to the heat exchanger. We would like to produce the superheat steam by remixture, right? Mix with superheat steam available from second source is 401 atm. We mix the feed vapor of water, right? 1150 at 1 atm with the superheat of vapor water at 400 Celsius 1 atm. That's right for this case. That's 1 atm also. 400 Celsius 1 atm. This is 1 atm. And saturated is 100 Celsius. Yes. Because we know this is the set steam. The set steam at 1 atm. The boiling point or dew point should be 100 degrees Celsius. Steam is mean water in the vapor form. Okay. You know input, you know mass input, you know pressure and temperature of input steam. You can calculate enthalpy of input. Right? You can open at 1 atm, you can open at 100 Celsius. Okay. The second steam, you know input is 400 degrees Celsius and 1 atm, and also you can calculate the enthalpy from the steam table. This is set steam, it is superheat, and you don't know mass of the superheat water. Okay, it denote as the unknown. After mix, you get the superheat of water at 300 Celsius, right? At 300 Celsius, and also 1 atm. You know temperature, you know pressure, you can calculate enthalpy. And you don't know mass, right? You don't know mass. Okay, it's M2 is unknown. For this case, we have two unknown, but we have only one component. So we have two unknown minus one component balance or one species balance is 0. 1 degree of freedom. You cannot solve only the material balance. That's why you need energy balance help for that. Okay, the first step you have to calculate the property of the input, enthalpy of the input at 1 atm or 100 Celsius. At 100 Celsius is approximately 1 bar, is 1 atm. The enthalpy of steam is 2676. Right. Get this? 2676 kilojoule per kilo. And the property at input of superheat steam at 400 Celsius 1 atm. This is the 400 Celsius 1 atm. 1 atm is approximately 1 bar. That's right. And it's 400 Celsius. You get enthalpy 3278. Right? This. Right? And the last term is 300 Celsius 1 atm. This is 1 bar is approximately 1 atm. It is 300. That's right. You get 3074 kilojoules per kilogram. Okay. You know entropy input. You know entropy output. You know temperature. Right. Now you can apply for the material balance and energy balance. Okay. The first step, you make the mass balance of water out the mixer. Right? Out the mixer. How about water? We have water input 2 feet and 1 output. That's right. Input 1150 plus M1 equal to M2 because there is no generation, no consumption, and no accumulation because we assume input equal to output. It is the same. It to the system equal to it or equal to flow rate output the system. There is no accumulation. Okay, we get 1150 plus M dot 1 equal to M dot 2. This is mass rate balance. And how about energy balance? And then you call the general energy balance equation Q minus W equal to delta S equal to delta S plus delta EK plus delta EP. For this case, there is no Q because the adiabatic process. That's right, it's a adiabatic process. No Q. Right, because the adiabatic body. And there is no Q between system and environment. There is no heat transfer. Q equal to 0. And there is no sharp work. There is no kinetic energy. There is no potential energy. Okay. Finally, you get delta S equal to 0. Delta S equal to 0. And you know, right, delta S equal to summation MS out minus summation MS in. Right? Or MS out. How about MS out? This is MS out equal to MS in. That's right. Okay, you get in equal to out. Input we have two stream. That's right. This input. Okay, the first stream is the first stream, and this is the second stream M1. That's right. 1150 multiplied by S 2676 plus M1 multiplied by S 3278 equal to M2 multiplied by S. In this case, we have two equations, two unknown M1 and M2. M1 and M2. You can solve for this simultaneously. And then you get M1 equal to 2240